You know, in science, there are some truths that just feel absolute. They're like these giant walls built centuries ago, and we're all told they're impossible to break. But every once in a while, someone comes along and gives that wall a little push. Well, today, we're going to talk about a claim that might just bring a 200-year-old wall in mathematics tumbling down for good.
I mean, just think about it for a second. What if a foundational problem, one that has defined the very limits of algebra since the 1820s, wasn't a limit at all? And we're not talking about a small step forward here. This is a potential leap over a barrier that mathematicians thought was totally permanent.
For 2 whole centuries, this one challenge has been a cornerstone of higher algebra. It was almost like a map with a giant "Here be dragons" sign on it, telling mathematicians, hey, you can go this far, but that's it, no further. Entire fields of study were built in the territory before this wall.
So, to really get a grip on the scale of what's being claimed here, we first need to understand the wall itself. Let's head back to the 19th century.
And here it is, the Abel-Ruffini theorem. Basically, what it says is that there's no single catch-all formula using simple tools like square roots or cube roots, which are known as radicals, to solve any and every polynomial equation once you get past the 4th degree.
And look, this wasn't some casual suggestion. It was considered a proven, cold, hard mathematical fact. Generations of mathematicians learned it, they accepted it, and they worked within its boundaries. For all intents and purposes, it was the final word on the matter. Case closed.
But why? What was it that made this problem so fundamentally impossible to crack? Well, the reasons are all about the tools mathematicians had at their disposal. See, the classical methods, the ones that relied on things like square roots, were powerful for sure, but they had their limits. When you tried to use them on equations of the 5th degree or higher, the underlying structures, as described by what's known as Galois theory, just became way too complex. The math would explode into this absolute chaotic mess of terms, far too vast for anyone to manage.
So here's the bottom line. Instead of getting a perfect, clean, elegant answer, a beautiful symbolic one, mathematicians had to settle for close enough. They used super powerful computers and clever algorithms to get approximations, but the exact, pure algebraic truth? That was always just out of reach.
But what happens when someone just flat out refuses to accept close enough? Well, that brings us to the central figure in this incredible story.
Meet Professor Mourad Sultan Ezouidi. He's a mathematician who has dedicated decades to this very problem. He looked at that 200-year-old wall and saw not an end, but a challenge.
And in his own words, it's pretty clear, but I have never accepted that limitation. He saw the problem not as some fundamental limit of algebra itself, but more like a historical misunderstanding, a boundary that was only defined by the tools they had at the time.
So how in the world does he claim to do it? Well, the key is that his approach is just fundamentally different from anything that came before.
Okay, so this table really lays it all out side by side. On the one hand, you have the classical methods, which said impossible after the 4th degree. On the other, you have Ezouidi's theorem, which claims to get exact symbolic solutions. Instead of those old radical expressions, it uses something new called recursive discriminant structures. And maybe the most profound difference is the whole philosophical outlook. The old way accepted limits. You could call it mathematical fatalism, while this new way just completely rejects that idea.
So what exactly is this new process? Think of it less like a single key for a single lock and more like a method for solving a really complex puzzle. Instead of one big formula, it's a step-by-step recursive process. It takes a piece of the equation, transforms it, uses that new piece to transform the next one, and on and on. It's like a chain reaction that ultimately forces the equation to reveal its own hidden exact roots.
And the claim here is that this new framework can actually tame a mathematical beast like the 9th degree polynomial you're looking at. By applying just the right transformations in just the right order, it can produce exact verifiable roots. Again, we're not talking about getting close enough here. This is about nailing the precise answer every single time. Now, this is super important to understand. The claim isn't that Abel was wrong. It's that his theorem perfectly described the limits of the toolkit they had back in the 19th century. Ezouidi's work basically suggests that, hey, if you invent a new set of tools, the boundaries of algebra itself can actually be expanded.
Okay, so let's just imagine this claim holds up to all the scrutiny from the wider mathematical community. What does it actually mean? What are the real-world implications?
I mean, the stakes here are just huge. This would completely redefine what solvable even means in math. It proposes that there is no upper boundary, that any polynomial, no matter what degree, already contains the structure of its own exact roots. You just have to know how to look for it. It's a key that could unlock an entirely new frontier for algebraic research.
At the end of the day, this discovery, if it's proven true, isn't just about finding an answer to a really old problem. It's about changing the very nature of the questions we're allowed to ask in the first place.
And that really leaves you with a final thought, doesn't it? This story is such a powerful reminder that sometimes the greatest barriers we face are just the ones we've been told over and over again are unbreakable. It really makes you wonder, what other impossible problems out there are just waiting for someone to reject the premise and find a whole new way forward?